keyboards on this computer. Thank you. Yeah, I need a personal assistant, definitely. And it's always you that reminds me. So thank you. Okay, so what? Again, we've been looking at some amplifiers and doing some math to get equations for gain, for R in, for R out. The reason why we're finding those is, I have to get rid of this, that's what's going on, is to design amplifiers. And when you're doing analysis, somebody gives you the circuit and you find the current and the voltages, and then you go and you find the gain. So you got the circuit, you find the voltages and currents, and then you find the gain. And that's the opposite of when you're doing design. First, somebody has to come to you and say, I need a circuit that does this specific thing. And that might be you need to have a gain of this, of 1200 or minus 1200, or it might be, oh gee, I need to connect these two circuits together. This circuit needs to have an R in of a certain amount. Maybe it's the output of the entire op amp, so maybe your boss will come to you and say, oh, I need an R out less than 100, something like that. Then, so now you have your specifications. Now, we've mostly been working with BJTs, and today we'll continue with BJTs, but you'll see MOSFETs throughout the quarter, but not today. First you say, okay, did they ask for an infinite anything? The only time you can really get an infinite anything is if you use a MOSFET, because the gate current is 0. So that Rin looks like an infinite number. But so if there's something that asks for an infinite anything, they're probably talking about MOSFETs. Then you pick the topology. In the last homework, you saw 3 different flavors. You saw the common emitter, common source, common emitter, common gate, common base, and common collector, common drain. So if you did simulations, and you probably saw that each one has at least one characteristic that's different than another. And so depending on what the specifications are, for example, if your boss asks you for a big gain, do you want to use a common collector? So if your boss asks you for a big gain, do you want to use a common collector?
No.
No. Why is that?
I think common emitter has the best gain, especially with an active load.
Yes, exactly. So that's what I mean by pick a topology. So you have to go to the single transistor amplifiers, pick one of those that is most appropriate for the specifications your boss gave you. And then you do your small signal analysis. If your boss asked for gain, you've got to take whatever circuit you decided to use, find the equation for gain. So that's where you do your small signal analysis. That's for a common emitter, it was your minus GM. Well, actually, common emitter and common source. It was a minus GM RO in parallel with your resistor. And so now your boss gave you the gain, and now you have an equation for gain. You set them equal to each other. And in the gain equation, there's the currents and resistors in that equation. There's like probably going to be 2 unknowns in that equation. As a designer, you have to pick one of those values and then solve for the other. Okay. So these steps up top here, you get the specifications, you pick whether you're using MOSFETs or BJTs, then you pick a topology circuit that has a possibility of satisfying those specifications. Then you use that circuit, you find an equation for whatever spec was given to you, set the value that was given to you equal to that equation, and solve for stuff in the equation. I know that went by kind of quick. These steps are on the single transistor amplifier slides. And when I say single transistor amplifier, if you look at a common emitter with an active load, you see 2 transistors there. But that is still considered a single transistor amplifier. It's just that the load is made out of something that made out of a transistor too. But common source, common emitter, any flavor, common collector, common drain, common base, common gate, those are all considered single transistor amplifiers, even if they have a second transistor somewhere in their circuit. Okay, so just on these first 4 steps, are there any questions? Okay, again, for some reason, it's not letting me set the groups up before we meet. So let me set up groups. I'm going to give you a design problem to work through with your group. Get rid of all of these. Well, I'm not quite sure why this didn't. Somehow my folder got closed, so I have to reopen. Sorry. And 20, 308, and okay. So I'm gonna. Here is your challenge, and I'll send it out to the group behind a window. All right, so your challenge is to make a common collector. This is weird for your boss to tell you a common collector. How about we'll call it an output stage, but all the output stages we've talked about so far are common collectors. So your job is to make a common collector. With just a second, I gotta move all this stuff out of the way. With an Rin greater than 90K. So your first spec is Rin is greater than 90K. Do y'all have that? Okay, so your Rin is greater than 90K and your R out is less than 50. So your Rin is greater than 90K and your R out is less than 50 ohms, not 50K ohms, but 50 ohms. Okay, so you got those are 2 specs. Oops, sorry. Okay, so those are 2 specs. The other specification is that the supply voltage is 5 volts, but the input voltage to your common collector, so your input voltage to your common collector is at rest is 3 volts. So you want to design for a V in of 3 volts to your common collector. So any questions on the specifications?
Can you repeat the last one, please?
Okay, so supply voltage is 5 volts and your voltage in is 3 volts.
Thank you.
Okay, and then the model file is the model file we've been using in homework, the 650. So I'll send the specs out over and over again to the groups, but yeah. Any questions on the specs before you go into breakout groups? Okay. And a lot of these, there'll be an infinite number of, oops, where's my groups go? There'll be an infinite number of solutions. So if you get a little different answer, but it still gives you an Rin greater than 90K and an R out less than 50 ohms, then it's a great solution. Okay. So, too many windows. Oh, that's interesting. One of the rooms, everybody has a first name that starts with J. Oh, and 2 people aren't there. Okay. We'll do something with that. We'll fix that later. And sorry for having to take this time. I'll ask the tech support people why that button doesn't exist for me. This is too slow. Okay, second to last room. Not here. Okay, and there's one person that isn't in the room, but I need to go back and search for that one. So Beautiful. Hi all.
I think.
How are you
Hello.
doing?
Hi.
How are you doing? Any questions?
The announcement only shows up for like 2 seconds, so
Oh. Okay. What's a good way to do that? Should I just keep resending it like over and over and over again?
we can still access the like main chat.
Oh, okay.
But I don't think it pops up there.
Whoopsie.
The announcement doesn't, but
Darn it. It didn't I control C'd it. It didn't work. Okay, I'll send that out again there. Do you have any other questions?
Not at the moment.
Okay.
Oh, right. Oh, what happened?
Hi there.
Hey,
Any questions?
um, actually just starting right now, so I had a phone call.
Okay.
But,
Okay.
I can't speak for everyone else though.
So far?
I had a quick question.
Mhm.
So I'm working on the schematic, and I'm thinking like an emitter follower is a good idea. But are we
Perfect.
looking for a specific gain or anything like that, or
It's
do you
not in the
have-
specs, so
so
your
it doesn't
boss
matter?
doesn't care. Yeah.
Okay. For the emitter follower, I'm broke it down into like the small signal model, where
Perfect.
I have an RE on the emitter.
Mhm.
And I've grounded everything, but now I'm getting RE and R naught in parallel, but I don't remember how to calculate R naught. Is there like, does it matter?
You shouldn't get an R naught in parallel.
If we ground VCC, which is attached to the collector, right?
Mhm.
Then wouldn't
Make
that,
sure, here's a big hint. Make sure to do all the simplifications.
okay,
And actually, I forgot to give you all the equation for Rn, so I'll send that on chat next.
okay, thank you.
But yeah, make sure you do all the simplifications.
Okay, yeah, I might have to re-look at what I did.
Okay. Let's see. Hi there.
Hey, Professor. I guess I didn't do any equations. I literally just changed my circuit to like having Vn of 3 volts and VDD of 5, and I ran it and it worked.
Okay, but that's
But-
not calculating.
Yeah.
That's experimentally. So maybe I should have added theoretically, or do the design on paper.
Okay.
Do you have any questions? I forgot to give the Rn equation. I don't know if the other labs have used the equation yet, so I just posted that to chat, so that should help.
Oh, okay.
I don't think people can see the chat when they're in the breakout rooms. Like we can see the notifications, but not the chat.
Okay. Sounded like but you can see the chat now, right?
Yeah.
Yeah.
Okay. It sounds like the notifications don't stay up long enough.
Yeah, sometimes.
Okay, so I'll just keep sending it. Oh my. I can really see, that's a baby tooth right there. I never lost my baby tooth there. I can really see it. I never look at my face from the side. Anyways, okay, sorry.
For R out, are we just using that R out equation we had last time, or is
Okay, so did we do the R out for a common collector? I don't think we did. So
oh no, we didn't.
part of this is yeah, doing that small signal analysis to find the R out equation.
Oh, okay.
So I gave you I can keep sending that.
Oh, I saw that. I can see
Okay.
it now, but other people.
Yeah, I broadcasted it like 20 times. Probably annoying people, but yeah. So you have the equation for R in, and you need to find the equation for R out. And the hint there, and so that's a perfect place to be looking, but the hint there is to make sure you do all the simplifications. Remember, there were 4 simplifications. Ground DC sources. If there's 0 volts across a resistor, get rid of the resistor. If VBE or VGS or VSB is 0, get rid of the current source. And then what's the 4th one?
Nope.
I wrote it as if GM is constant, then VNI is proportional.
Yes. So GM is actually usually going to be constant, is always going to be constant. So that those current sources are actually acting like a resistor. And what size resistor are they acting like?
A large one?
Mm.
Oh, sorry. Did you mean like relatively, or?
There's an equation that you can, there's actually an equation for the size of the resistor.
V over GM times P? Oh, 1 over GM, sorry.
1 over GM, exactly. Yeah, so make sure when you use your small signal model, replace the transistor with a small signal model and try to come up with an equation for R out. Make sure you do all the simplifications.
Okay. Yeah,
Like
my Wi-Fi was cutting out, so I didn't catch like the first 6 minutes of your lecture.
Okay. I'm sorry.
No, it's not your fault. I don't know what's going on today all of a sudden.
My Wi-Fi's been, I shouldn't say, but my Wi-Fi's been good.
That's good. Yeah, I don't. Maybe I shouldn't say anything either.
No. Okay. Looks like people are coming back, but I would bet that there were some, didn't quite get to a solution in most cases. So what was your first step? What's the first step again? Are you sure?
0 to the DC sources.
That's the simplification when you're doing the small signal analysis, but when you're doing a design,
Drawing the small signal model.
okay, but what about from your boss?
Oh, the specs.
Yeah, you need to find the specs. And in this case, there's a spec for R in and there's a spec for R out. So that means you need equations for R in and R out. Okay, but let's see. Let me broadcast out them talking. Come on back. Okay, so that's getting the specs. Okay, and then what was 2? What was 2? It was the BJT or MOSFETs. And this time I told you, which one is it?
BJT.
BJT, yes. So that worked pretty well. Yeah, so this time it's BJTs, okay. And then what's number 3? So for this one, it has a pretty high R in and a pretty low R out. So in future design problems, you'll go to your results of your homework and pick one of the single transistor amplifiers. So which amplifier has a big R in and a small R out?
Common collector.
Common collector. So this is, I call this topology. And that is a common collector or emitter follower or impedance transformer or level shifter. They're all the same circuit. They just have many different names. Common collector. Okay.
For number 2, did you choose BJT just because that's all we know, or is there a design reason for that?
I told you to. I said use a BJT that we're using in class, and that happens. For those of you in the 307, you already heard the story. But when I was working in Japan, they accidentally bought like 1 million resistors, like 1 million. I forget what size they were, but I just made them 1K, like 1 million 1K resistors. So our boss came to us, said, build this thing, but make sure it uses 1K resistors. You know, so sometimes your boss has weird recommendations. And this one, I told you, hey, use the model from class, and that just happens to be a BJT. So I told you in this case.
There was a whole run of audio amplifiers in the 70s that used a weird Russian FET because some company bought like 1 million of them for like nothing.
So yeah, you might get weird requests from your boss. And then topology, now you've got your circuit, you've got your specs. Now you need some way to solve for, what's the most important thing usually when you're designing to find? What's a good first thing to pick when you're designing a circuit? What does the most damage?
The current.
Current, yes. So from here, you have to find the equations in order to solve for current first, and then resistors, whatever else might be needed. So what equations do you need to find? You've picked your topology, so your common collector. So you've got your circuit. your V out. You've got your circuit, and now you want to find some equations. What equations do you want to find? Which specific equations do you need?
Collector current.
Okay, well that is definitely, that's one of your large signal most important values. You usually try to find that first. So if you have an equation with two unknowns, let's say current and a resistor value, don't pick the resistor value. Pick a current that makes sense for your transistor. Like these transistors go from like 1 milliamp to I don't know, 100 milliamps. So you'd pick an IC somewhere between there and then solve for R, because the current's the most important thing to pick first to have in the right range. Okay, but for this, you're gonna need to find some equations. You're gonna do small signal analysis and find some equations. Which equations do you need to find?
R in.
Exactly. So whatever specs were given to you, those are the equations you need to find. So now you've got your circuit. You need an equation for R in, and you need an equation for R out. And once you find these equations, now you set it equal to, whoops, less than. Now you set them equal to the values that were given to you as specs. But you need to find these equations, and the way you find the equations for R in and R out is to do small signal analysis of your common collector. So questions on that, and I'll send you all back to your groups if now you have better direction. Any questions? Okay, good. Give this.
Actually, I
Okay.
have a question.
Okay.
So when you're doing R out, right, and you're doing, let's say, like V over I out, and the condition is like V in is grounded, or like it's 0.
Exactly.
If you're doing that in small scale analysis, what I don't understand is if you're grounding all the DC sources and you have no voltage coming in with the input, how would you get a V? Wouldn't V out just be 0? So R out is like, I'm a little confused as to how you're supposed to get a voltage.
Okay. Again, this is a single part of a superposition problem. And when you zero the DC sources, you get weird things. You get things that don't look like any circuit that you would actually build. But these are trust the model. We went through and saw how this model predicts or calculates, I'm not sure the right word, moving signals only. So it's just telling you about the moving part of the signal, and you just kind of have to believe that that model makes sense. So even if I get a weird circuit, it's okay that it looks like a weird circuit. One thing, I don't know if that answered your question, but yeah, you get some very odd looking circuits, and you just have to, if you zeroed the right things, that is actually what it's supposed to look like.
Okay. So be expecting an R out value even though we're grounding the input signal.
Yes, the dependent current source can still force current through your circuit, even if you have grounds on both ends of it, which is usually where the true weird looking things happen. One other thing is that when you do the small signal analysis to find R out, make sure to go through all the simplifications. So there's 0 DC sources, like, as you said. If there's 0 volts across a resistor, get rid of it. If VBE equals 0, then get rid of the current source. And then the fourth one is the dependent current source. If you have GMX, VX, and then you have VX across it, this goes to a resistor of size 1 over GMX. So make sure you go through all of those simplifications when you're trying to find an equation for R out.
Yeah.
Okay. Let's give you like till 2:58, and then come on back and I'll give you the I'll show you how I did it.
Sounds good. Thank you.
Okay. All right, go on back and give that a second try in your groups. What, sweetie? What's wrong, sweetie? Okay, so it looks like almost everyone's back. Okay. Oh, Tristan, I'm sorry, I didn't put you in a room. Okay. So did the work here. I can just scroll it up since we only have a couple minutes. I'll scroll it up. But you have a specification for Rn, and I gave you that equation. We'll see where this comes from. I think I posted the video on where this shortcut version of the equation for Rn came from. And then you can replace R pi with its equation, the beta Vt over Ic that we found by taking the derivative of the current equation. And then part of your design decision is you're going to have to pick that resistor that goes below the transistor. Oops. So this would be Re. V out. Okay. But you know that Rn has to be greater than 90K. So you can set that equation greater than 90K. You also have some information about R out. And I'll do this just because we're out of time. I'll put up a video on how to find this equation. It's also on the slides, but I'll do a video for it too. And this is like a small resistance in parallel with a big and a big and a big. So what happens is all of these things are in parallel when you do the small signal analysis for R out, but GM is so much smaller, you can approximate this as 1 over GM. And that makes your math a lot easier. And you know that has to be less than 50 ohms. So this is a nice friendly equation, and you have a value for Vt. So you can massage this, move the IC over here and divide by 50, and you have to have more than a half a milliamp. So this is current right here. And then you have a value for that. So you as a designer get to pick any value that's greater than half a milliamp. So I just randomly picked one milliamp. And going back to this first equation up here, this equation for Rn, moved everything around so that Re equals, or I got Re equals this. This is just moving everything around and putting in your value for IC. That gives you 430 ohms for Re. And actually, when you put it back in and test this out for IC, it actually gives you a little larger R out than you want. So you actually have to, a value that does give you a successful design is 425 ohms. But I'll make a video of this too. I'll just go straight through it and try to keep it short and go through the whole design. But the goal today was just for you to see that you get the specs, and then when you do small signal analysis, you find equations for the values that were given to you in the specs. That was the goal of today. So good questions?
Yeah, I had a question. How did he get the beta value to be 197? How did he figure that out?
That is in the model file.
Oh, it was given to you in the first place. Okay, that makes sense.
Yeah, so if you, again, go back to the MPS 650, this VAF, that's your early voltage, that's your beta, your VJs, your VB on if you need it. So you can get those values from the model file. Okay, any other questions? Okay. I think the next section I'll try giving more pictures earlier on and then send them out to the group. But wanted to see if you could work that out. So sorry about that. But yeah, again, I'll post a video. Okay. Any other questions? And that's all I got.
How did you know that 1 over GM was going to be smaller than all those other resistor values?
It's so GM is often 0.1 to 0.01. So 1 over GM should be something like 10 or maybe 100. And for RO is VA over IC. VA is already 100. And if you have a current that's less than an amp, that's going to be very much bigger than 100. RO is generally the biggest the biggest value in your small signal model. And 1 over GM is usually the smallest resistance. R pi is usually in between the two, but also pretty big. Yeah, if you work these out, you'll end up with something like this will be something like 10K often, and this will be something like 100K. This will be something like 10 to maybe 100. And this right here, in our design, it's actually pretty small, but ideally it would be bigger, like a 1K or something. So you're comparing like 10 or 100 to 1,000, 10,000, or 100,000 usually.
Okay, that makes sense.
Yeah, GM is often 0.1 to 0.01. Okay, maybe we'll go for another design problem on Friday.
Thank you, Professor.
Okay, is that okay, Amani?
Yeah, I think so. I'm just gonna make sure I got to the part where for the small signal model we just had R out in parallel with R emitter for the like after you do the simplifications on it, but I didn't get to any of the math yet.
Okay, the current source doesn't disappear. That's where this 1 over GM comes from. So check that out. It's not just RO in parallel with RE. A lot of groups got that though.
Okay, I will double check that.
Okay.
Thank you.
Okay.
So, Professor, the reason why you were able to turn the dependent current source into a resistor was because, again, with the R out case, you're grounding V in. That base voltage is now 0. The emitter voltage is still the emitter voltage. So VBE is the same as the voltage across the dependent source because you're grounding the DC source.
Exactly.
Okay, so the voltage is the same. It's still, I guess technically it's negative VE or whatever. VBE becomes negative VE whether it's across R pi or across the dependent source itself.
Exactly. Yeah, so it doesn't have to necessarily be shorted, even though if both the tops are ground, it's like they're shorted, but it doesn't have to be a circuit where that's shorted. It just has to have the same voltage.
Okay, got it. So just B needs to, the base voltage just needs to be the same as the collector voltage then, and then it becomes a resistor essentially.
Yeah, that's a good way to look at it.
Okay. Thanks, Prof.
Okay, see you later. Oh, I see what it's telling me. Wow, a lot of people taking the day off. Trevor, is there something on your picture? Is there something on your shoulder?
Yeah, it's not a corsage, but what's the other thing? That was like from a high school dance.
Oh, you look very, very, what's the word I want? Smashing is the only word it's coming to mind. But
Thank you. But my date was a photographer, so that's why.
ah. You know, my eyes aren't great, and the picture's small, so I get all sorts of entertainment out of pictures that aren't supposed to be entertaining. Like, it actually looks like there's a monkey on your shoulder from this distance and with my eyes. Okay, I guess it's well, 9 after. Not sure that anybody else will be here today. Nine, 10. Okay. So I don't have any business to talk about, I don't think. Homework's posted. If we don't get into a topic that's on the homework today, I think we actually have covered most of them, but if we don't get to a topic today, then I'll make sure that we do it Friday. That's all I have. Really. I gave the other section kind of an update on the faculty meeting about, you know, half of the faculty not wanting to come to campus in the fall and half insisting that we must. So still no decision on what's going to happen in the fall. But let's see, do you have any questions on the course or anything else? Nope. Okay. Then today, doing a design problem. And again, 307 was supposed to be like 306 and 307. They weren't necessarily supposed to be design classes. They were more analysis classes. Ideally, 307 started to be a design class. But our goal here is somebody comes to you and says, I need this circuit, and you design the circuit for them. So let's see. Where did I start on this? Let me see if I have any helpful stuff here. Okay, I remember where I started. So let's do, again, saying this in words isn't all that useful. Working through a problem is where these steps finally make sense. So I'm just going to go through like the first 5 steps, actually 5 or 6 steps. And then I'm going to give you a design problem and let you all work it out. Okay, so again, mentioned last time, your boss won't come to you and say, build me a common emitter. Your boss will come to you and say, hey, I need a gain of minus 1200. Or, hey, I need an R in. If they're talking about 2 circuits that have to be put together, say, oh, I need a circuit that does this, but it has an R in greater than a certain amount. So it won't load the circuit that it's being connected to. Or maybe it's the last stage in an operational amplifier, so it needs a really low R out. So your boss might say, hey, I need an R out less than 25 ohms, something like that. So your boss will bring you a specification like that. This is my R in, this is my gain, and or this is my R out. Okay, so those are the specifications you need from your boss before you can start to build. Second step that I have on my official list, and these are in the single transistor amplifier slides, so if you want to look this up. Second is to pick the technology, and if somebody says, oh, this has an infinite RN, what do you think you pick? MOSFETs or BJTs?
MOSFETs.
MOSFETs, yeah. Nothing else is going to give you at low frequencies an infinite RN. Okay. There actually is a little gate current that seeps through, but it's close enough to 0 that we say 0. Okay, so now once you've picked your transistors, And technology actually has a kind of a broader meaning. You know how you have, hi Raul.
Oh,
Okay, but you know how there's different model files? Every model file has a little bit different values in it. If you need a particular behavior, you might have to go, you might say, oh, this model file has a really low beta. That's going to pull a bunch of current, so I don't like that model. So this technology, this number 2 right here, it's a little bit more than whether it's BJTs or MOSFETs. But for this class, I'd probably give you the model information. So you wouldn't have to go look through 1,000 different transistors and find one that gives you the exact transistor behavior that you want. But yeah, a little broader meaning than BJT or MOSFETs, but we'll use that as BJT or MOSFETs in this class. So topology is, let's say your boss says, I need a high gain and a high RN. Remember from last homework? Or a high magnitude of gain and a high RN. Do you know what single transistor amplifier you might use? If there's gain, that reduced the number. So there's 3 different types of amplifiers: common source or common emitter, common base or common gate, and then common collector or common drain. So if somebody says, oh, you need a gain, what does that get rid of?
common base.
If you want a gain, which one do you get rid of? So which one has the lowest gain? I should say
Common
it that way.
collector.
Common collector. Yeah, the common base has good gain, so that would still be in the list. That would still be in the running. But if you say you need big gain, then you get rid of the ones that don't have a big gain, which is the common collector. So you know that one's out. And then they say, okay, and then I need a big RN. Which one does that get rid of?
Common base.
The common base, because that has a low RN. And so now you say, I've picked my topology. It has to be a common emitter. So that's the way to kind of use the specs to decide which type of single transistor amplifier you want to use. So up to there, good? Okay. So now we pick the topology. And now you do small signal analysis. And it's not just, you don't do everything. Like if your boss just gave you a gain and an R in, you don't need to find R out because your boss only gave you specs for RN and gain. So when you do small signal analysis, all you'd have to solve for is RN and gain, and you'd be done. And if you pick MOSFETs, what's the RN? Infinite. So you're done with RN. So really the only small signal analysis you have to do, if your boss gave you gain and RN for a MOSFET, is the gain equation. And you already know that. That's your minus GM, RO parallel with R. Okay. So now you've got your specs, you've picked MOSFETs, you picked a topology or common source because you need a big gain and a big RN, and you did your small signal analysis to come up with an equation for whatever your boss gave you specs for, in other words, your gain. Now you take the value your boss gave you for gain, your equation for gain, and set them equal to each other and solve for the unknowns in your gain equation. Now, what's the first thing you usually pick when you're doing design? What's the most important thing to pick?
I see.
I see. Yeah. So if you have your gain is minus 12,000 equals to an equation that has like an unknown R and an unknown I, picking the wrong value for R won't make your circuit burst into flames, but picking the wrong I would. So you usually go back to the transistor, say, oh, this transistor is good from 1 milliamp to 100 milliamps. Okay, so I'm going to pick somewhere in the middle there. Let's pick 5 milliamps. And then find the R that works with that current. Okay, so if you have 2 unknowns and one of them's current, pick pick the current from your knowledge of what makes the transistor happy. Okay, so there's that. And then once you have your current and your resistor, now you can actually draw the common emitter or common source. Sorry. Okay. Questions on those steps for design? Okay. These are kind of opposite of what you've been doing in other classes. So for steps in analysis, they usually give you the circuit and say, hey, figure out the currents and voltages. And once you figure out the currents and voltages, now you can go figure out what the gain is. So it's the opposite direction. You're given the circuit, then you find the voltages and currents, and then you go and find the gain. So exact opposite direction of design. Okay, so good up to there. All right, any questions on these kind of the flow, the steps you go through to design? Okay, then we'll move on to, so there's our design, and I have where's my pen? There's my pen. I'm gonna give you some specs. V supply. Right? When I say V supply, it's the same as VDD or VCC. That equals 5 volts. And your V in for your common collector, that at rest sits at 3 volts. So let's say you're connecting it up to a common emitter. The common emitter, the output sits at 3 volts when it's just biased. So that's going to be your input. You want an R in greater than 90K. And you want an R out less than 50 ohms. Not 50K ohms, 50 ohms. Okay. So those are your specs. So I just took care of step 1 for you. And I'm actually going to take care of step 2 for you because I want you to use the model that you have been using in class, which is the MPS 650. So if there's any values that you need, go to the model file for the MPS 650. Okay, and the last thing is that I think, well, I thought that the labs had already gone through this equation, but I'm not sure if they have now. There's an, my pen stops working again. R in, I don't know what's going on. There we go. R in equals R pi plus R e 1 plus beta. Oh, so I guess I kind of did a second step. Let's say your boss told you that it was an output stage. And what's important about an output stage?
Has no output impedance.
Yeah, low output impedance. So what of your single transistor amplifiers, which one has a low output impedance?
Common collector.
Yes, so that's how I just realized that it's sitting here, answer sitting here. But yeah, if you look at a common collector, the equation for Rn, I'll just give this to you. I posted a video on Canvas. This is a shortcut version of the Rn equation, but it's pretty accurate, works well. Okay, so your job. So I'm your boss. I'm putting like the power arms right now, so I look like a boss. Is to design this output stage. And I'd like you to work as a team so everybody sees the work that you do. So everybody can follow along. So work as a team and make sure everybody can see what you're doing. I think I've got everybody in the picture now. And instead of going to a breakout group, because I'm having trouble getting pictures to a. Oh wait, you know what? Was I not sharing? No, I'm sharing, aren't I?
Yes, you are.
Okay. Usually there's a green border, but there's not this time. Okay, so I'll leave this up. If you go into breakout rooms, then you can't see the screen, I think. So go ahead. You are the design team, and I'll just sit here and be a bug on the wall. Okay. Yeah, this one. Make sure you use all your simplifications. Okay, where did you find that?
The beta?
So your equation for IC, you
Oh,
got,
that's not me.
oh, okay.
Sorry.
Okay, let's go back a step, because usually you pick IC after you get your equations, and you have this is perfect. I mean, this is what you want to. This is exactly where you want to go, but give me the reason why you drew the small signal model. What was that? Why did you draw the small signal model?
I guess I did it just for fun. I don't know.
No, it's the perfect. It's exactly what you want to do. But let's go back to the steps. So the first one are the specifications. So I think they're good. So check on that. Okay, and then I told you to use a BJT because we had the model file. Okay, and then the topology, you picked a common collector because I said output stage. And then what's the next step?
I guess we would want to choose an IC.
Okay,
Right.
but so step 4 is finding equations, but equations for what?
Oh, RN and R out and stuff.
Exactly. And I gave you the equation for Rn. So what's missing?
R out.
Yeah, so you need an equation for R out.
Can't we just approximate that with negative GM or 1 over negative GM?
But you have to find that equation. I think we did that the other day, but just for review, go ahead and find R out for that. We already did it once, but do it one more for the people that weren't here. So how do you find R out?
I'm writing the general equation for it right now.
Okay, but to find that equation, go through the small signal analysis.
God damn it, sorry.
Okay, good. Zero to Vn. Okay. Oops. How do you scroll this thing? How do you move it over?
You could do, if you're using a touchscreen, you can use 2 fingers and slide around. I don't know about with a mouse though.
Okay.
On the right, there's a little menu with a hand. If you click on the hand, it allows you to grab and scroll.
Okay. So I agree with your picture, but you lost the ground on your last. And it's always good to mark all the terminals. So how about going back to your first drawing and marking V out? So V out's missing from the diagram. It's a simple fix, but a simple addition, I should say. Okay, good. And then for the next diagram, there's two, I always write in VBE also. In this case, you don't need it, but sometimes when you start putting resistors in parallel and moving them around, you lose track of where VBE is. And if the dependent current source still depends on VBE, then it's nice to keep track of that. But okay. Okay. VBE doesn't equal 0. So where's V out on the last diagram? Or the second to last diagram? Yes, okay. So V out isn't grounded, so there's not 0 volts across R pi or RO parallel R. So I have to keep that. Okay. Do you want to, can you give an explanation why the current source goes to 1 over GM? Anybody?
It's 1/GM is much smaller than R naught and R pi. What? Yeah.
How about going up and say why the current source can be turned into the resistor?
Oh, excuse me, sorry. Because VBE times, oh shoot, it's like VX over GM times VX. But VBE and VN.
So since VBE equals negative V out, it's that voltage across where that, well, because with the one of the simplifications is when you have Vx across the current source, and it's Vx times GM, you change it to the resistor of 1 over GM. I didn't explain that very well, but I guess. But
No, good job. Okay, and the one circuit that we looked at that we did this for earlier was a diode connected transistor, and that was actually shorted. It doesn't have to be shorted. These wires don't, I mean, these are both ground, so it's like they're shorted anyway, but if the voltage across this resistor equals the voltage across the current source, then you get to reduce it to a resistor. So this voltage just has to equal this voltage. And the way you can check that is the base has to equal the collector because the emitters are shared between the two. So you really just have to check the collector and the base and see if they're the same. So is that good? All right, then you got down to that. Yes. So it looks good. Okay, so you have an equation for R out now. Okay, so what happens next?
Pick a current.
Okay. I suggest you have an equation for R out and you have an equation for R in. I might just write those two equations down. Well, that's hard. I see somebody's writing it up top, but I totally didn't see that because it was out of the screen. That's oh. Okay. Does everybody see where it's being written?
Yeah.
Okay.
I don't, but I think it's because I'm using a phone. So
Okay.
I'm trying to access the computer right now to see it.
Okay. It's up under the first small signal diagram. It's right up, just a little bit lower and to the left.
Got it.
Okay. And so IC has to be greater than that, right? Okay, it looks good. Okay. So there's two ways you can go from here. You've got that other messy equation that you wrote above, the Rn equation. I mean, you could plug in something for this, or you could pick an IC. As designers, what do you want to do? Okay, and then what do you know about Rn? Okay, looks good. So, design team, what's your next step?
Should we just pick an IC greater than 0.52 milliamps?
That's what I did. I got lazy.
Okay, so we don't need to find like an upper bound to IC or anything.
Well, it's kind of like if you pick a one milliamp, say, then it's more than 0.5, so your resistances are going to drop. But if you try it and it works, for these transistors, I forget, I think they start at 1 milliamp. So I think 1 milliamp is the lowest current you can actually use with these transistors and make them happy.
So let's choose 1 milliamp then.
So will IC not change that much when this is operating? 'Cause-
IC will change, but you generally design for the at-rest
okay.
position. Your boss might tell you that in the entire operating range, it has to be, you know, less than or greater than 90K.
Thanks.
Is it less than?
I don't know. I always get confused switching inequalities.
Yeah, we probably just divided both sides by 193. So I think RE is still greater than that. And what did I get? Okay. Yeah. So if you make RE bigger than that, then you're good to go. But let's do one more sanity check. So what other information did I give you?
R out. Oh wait, never mind.
VN.
Yes. Actually, I didn't check this, and now I'm getting worried that this will work, but let's give it a go. So if you know VN, what else do you know?
What V out should be?
Yes. And if you know VN for a common collector, how do you figure out what V out would be?
Do you just do VN minus VBE?
Yes. And where do you find VBE or VBE on?
In the model file.
Exactly.
This one, it's about 0.7.
0.7? Okay. Sorry. Okay, like 0.777 or so. Okay, so that would be 2.23. If you put 2.23 volts across a 438 ohm resistor, what do you get, just out of curiosity?
5 milliamps.
Oh. Okay, so if you're picking 1 milliamp as your current, then there has to be some massaging going on between these two. So that was, I didn't fully vet this problem, so I apologize. RE gets bigger. RE doesn't matter for R out. So you could just increase your RE. It won't affect your R out, but it will make your RN bigger, which is not a problem. So if you have that 1 milliamp as your current, then you'll actually have to make RE bigger. And you have an output stage with an RN meet specs and an R out that meets specs. So is this process okay? Got a thumbs up there?
Yeah.
Okay. Actually, I didn't even get near this point with the other class in an entire hour. So once again, we're quite far ahead of the other class. Let's see, what would be useful here? There's 10 minutes left. Do we want to try that? Oh my goodness. Okay, then I had it on the list, but I decided not to do it today. Let me see what else I had on my list.
I mean, some of us have an exam right after this, so ending early might not be the worst.
Okay, all right, that's fine. And I will put up a video on this just in case you want to go back and look at this, and I'll leave the whiteboard up. Okay, and those that don't have an exam, welcome to stay, ask questions. Okay, well, good job, good design job. You're hired. Okay.
Professor, I had a question.
Huh?
Would you be able to post a solution to this problem, or like what was on the screen for those who couldn't see the screen?
Okay, yeah, I'll do that right now. I'll make up a video and go through the whole design process.
Oh, thank you so much.
Oh, my pleasure.
I had another question.
Mhm.
You said that this class is ahead of the earlier one.
Mhm.
Sometimes it's I'm not able to make the 3 o'clock, but I can do the 2 o'clock.
Okay.
And it's okay for us to like drop in the other class too, right?
Absolutely, yes.
Okay. Just wondering.
Yeah, I'm not much of a stickler for, you know, those aren't real necessarily